Hey guys, this is Mrs. Harvin, and this is section 2 of chapter 4 in Algebra 1. We are going to continue to learn about inequalities. Our lesson objective for today is that you, the student, will solve inequalities using addition and multiplication and solve word problems with one-step inequalities. Remember that everything that we do, we're not just learning a bunch of mathematical steps just so we can solve problems in a book, but we are learning how we can use these skills to help us be better at having dominion over the earth and taking care of the Lord's creation. Let's talk a little bit about properties of inequalities. Just like with equations, remember equations are two expressions that are equal. Just like equations, adding or subtracting the same number on both sides of an inequality produces an equivalent inequality, having the same solutions as the original inequality. Now, you guys remember that if we have, for example, 3 equals 3, whatever we do to one side, if we add 2 to one side, we have to do to the other side, 3 plus 2. That way, our equation is still true. This is the same with inequalities. Whatever we do to one side, we're going to do to the other so that our solutions are still true solutions. The addition property of inequality states that, or holds that for any of the 5 inequality symbols, that whatever we add to one side, we add to the other. And that's true for our 5 inequality symbols, which were less than, greater than, less than or equal to, greater than equal to, or not equal to. So the addition property holds true for all of those inequality symbols. Stated this way, if A, B, and C are real numbers or expressions such that A is less than B, then A plus C is less than B plus C. Now you may be thinking, what does that mean? Well, let's put some real numbers in there and take a look. Let's take this expression, 6 is greater than 4. Here you can see we've got 6 little beads on our scale here, and they are heavier than these 4 little beads. It's greater than 4. If we add 2 more beads to each side, whatever we do to one side, we do to the other, we now have 8 is greater than 6. Our inequality is still true. Whatever we do to one side, we have to do to the other so that our inequality is still true. If we subtract 1 from each side, we get 7 is greater than 5. Again, still true. So the addition property of inequality says that, again, whatever we do to one side, if we add to one side, we have to do to the other so that our solutions are still true. And that's going to be the same for all 5 of those inequality statements. It doesn't matter if we're dealing with less than or greater than or not equal to. Let's take a look at this example. X plus 7 is less than 8. We want to solve for x. Just like when we're solving x plus 7 equals 8, we need to follow the same steps. We need to get this x by itself. Now right now what's happening to the x is that it's got 7 being added to it. We want to get rid of that 7, and the way that we get rid of a positive 7 is by subtracting 7, which you can see here. Now if we subtract 7 on the left-hand side, we also need to subtract 7 from the right-hand side of our inequality. When we do, we get x plus 7 minus 7, or x, is less than 8 minus 7, which is 1. X is less than 1. We would then graph that on a number line. Because it doesn't say equal to, we're going to have an open circle at 1. And because it says less than, our arrow will go to the left. Less than goes to the left. Less than goes to the left. So all of these numbers, if we were to plug these numbers back into our original inequality, our statement would still be true. Well, let's check and see. Negative 3 plus 7 is less than 8. Yep, 4 is less than 8. Negative 5 plus 7, that's 2, is less than 8. Yep, all of those work. And so we can take our solution set here, plug it back into the original equation just to make sure we followed the steps correctly. Let's try another one. X minus 5 is not equal to 3. Just like when solving an equation, we said it works for all 5 of our inequality symbols. We want to isolate this variable. Well, right now it's having 5 subtracted from it, and the way we get rid of a negative 5 is with a positive 5. If we put positive 5 on the left, we also need to put positive 5 on the right. And x minus 5 plus 5 is just x. And 3 plus 5 is 8. So x is not equal to 8. Notice that in each of our steps, our sign did not change. When we're just adding and subtracting, our sign does not change. Let's go ahead and graph that. If something is not equal to 8, it's going to have that open circle there on the 8. But any other possibilities, it could be. It could be 7, it could be 9, it could be to the left, it could be to the right. So we're going to draw arrows going both directions. Let's try this one. Negative 0.6 is less than or equal to x minus 0.4. Now, I'm not sure what this letter is right here in the presentation. I don't know what that is. So we'll just kind of skip over that and maybe it'll make sense as we go along. We want to get the x by itself. Right now it has negative 0.4. So we need to cancel that out by adding 0.4. Whatever we do to one side, we have to do to the other. By combining our like terms, we get negative 0.2 is less than or equal to x. If we flip that around, we get x is greater than or equal to negative 0.2. Notice that when we swap everything, it's kind of like we've just taken a piece of paper and flipped it over. Everything flips over, including the direction of that sign. When we switch sides here, it is greater than or equal to, so we do need a solid circle here. And it's greater than, there's an R and greater, which can remind us that we need to go to the right. Greater than goes to the right. So what happens if you multiply both sides of an inequality by a positive number? Try some examples and see if you can figure that out. What happens if you multiply both sides of an inequality by a negative number? Well, let's take a look at the rules for when we multiply by positive or negative numbers. The multiplication property of inequality has similar results for these three signs: greater than, less than or equal to, or greater than or equal to. But remember that when you need to reverse the inequality symbol when multiplying or dividing by a negative number. Remember when we first learned about negatives back in chapter 2, I believe we said negative just means the opposite. So when we're multiplying or dividing by negatives, it's going to change our sign to the opposite. We've got to flip that sign. Let's take a look at our definition. If A, B, and C are real numbers or expressions such that A is less than B, and we multiply it by a number greater than 0, then our sign stays the same. AC is greater than BC. Let's try some numbers here. We'll use 3 and 5 for our A and B, and let's say that C is 2. 3 times 2 is less than 5 times 2, which is 6 is less than 10. Right? That holds true. So when we're multiplying it by a positive number, number greater than 0, our sign stays the same. However, when we're multiplying it by a number that's less than 0, a negative number, remember negative just means that it's the opposite of a number. So then we need to switch that sign and make it the opposite sign. So let's say C was negative 2. If we don't switch our sign, let's see what happens. We get 3 times negative 2, 6, is less than, or sorry, negative 6 is less than 5 times negative 2, negative 10. 6 is less than negative 6 is less than negative 10. That's not a true statement. In order for that to stay true, we've got to flip our sign. Negative 6 is greater than negative 10. So when multiplying or dividing by a negative, we've got to flip the sign. Let's take a look at this inequality. 2 is greater than 1. If we multiply both sides by 2, we get 4. All right, let's take a look at another example here. We've got negative 3x is less than negative 9. We need to get the x by itself. Right now it's being multiplied by negative 3, so let's divide by negative 3. And dividing by negative 3 will switch our sign. Remember, when we multiply or divide by a negative, we've got to switch that sign. And when we solve for x, we get x is greater than 3. Well, if we go in and we plug in some numbers that are greater than 3 here, like a positive 4, for example, we get negative 3 times positive 4, that's negative 12, which is less than negative 9. So that is true, that works. If we hadn't switched our sign, And when we went in to check our answers, we would have gotten false statements. We're then going to go ahead and graph our solution. X is greater than 3. It does not say it's equal to 3, so we've got an open circle, and then greater than goes to the right. So any of these values, if we plug them into our original equation, will give us a true inequality. Let's try x divided by 12 is greater than negative 4. Now x is being divided by 12. We want to get x by itself. And the opposite of dividing by 12 is multiplying by 12. So we're going to multiply both sides by 12. And 12x divided by 12 is just x. 12 times negative 4 is negative 48. Now we don't switch the sign here because I wasn't multiplying by a negative 12. I was multiplying by positive 12. Even though this negative 4 was already here, I didn't multiply it by both sides, so we don't have to switch the sign. We only switch the sign when we are multiplying or dividing both sides by a negative number. We're left with x is greater than negative 48. So any number greater than negative 48, when plugged back into our original equality, should make a true statement. What about negative 5 halves x greater than or equal to 25? Well, right now x is being multiplied by negative 5 halves. So the way that we get rid of that is divide by 5 halves or multiply by the inverse. So we're going to multiply both sides by the inverse, negative 2/5. These will cancel. You'll get 10 over 10, which is just 1 when you multiply that out. And then over here, negative 2/5 times 25 is negative 10. Multiply the top. 2 times 25 is 50. Divided by the bottom, 50 divided by 5 is 10, in case you didn't follow that multiplication of fractions there. Please notice that because we multiplied by negative, we did switch the direction of the sign. So any number now less than or equal to negative 10 when plugged back into our original equality should give us a true statement. Let's take a look at a word problem here. How much money must be invested at 7% simple interest to produce an income of at least $875. So we want a yearly income that is either greater than yearly income. We want it to be greater than or equal to $875. Remember, our interest formula is PRT equals I, principal times rate times time equals the amount of interest. Let's plug in what we know. We don't know our principal. That's what it's asking us. How much money must be invested? We know the interest is 7%, 0.07, and we know the time is 1 year, and we know that we want it to be equal to at least $875. So we want 0.07p to be greater than or equal to 875. When we solve for p, we find out that our principal must be greater than or equal to $12,500. So if you're wanting to draw $875 in interest from the bank each year at 7% interest, you need to invest at least that much money. $12,500 or more must be invested. If you are an investment banker or a wealth manager, wealth portfolio manager, this is the kind of problem that you would be answering for your clients when they're trying to find out how much money they need to invest. Today we solved inequalities using addition and multiplication, and we solved word problems with one-step inequalities. We need to remember that whatever we do to one side, we do to the other, and that when we are multiplying or dividing by a negative number, we do need to switch the direction of our sign so that our inequality remains a true inequality. If you have any questions, be sure to ask me next class.